So let's continue with the two-pointer and sliding window playlist from the Strivers A to Z DSA course. But we're doing that. Hey, welcome back to the channel. I hope you guys are doing extremely well. So the problem that we will be solving today is subarrays with k different integers. So what is the problem stating? It is stating that you will be given an array. It will be containing integers. You'll also be given an integer k. Now your task is to count the number of subarrays. Any contiguous portion of the array is known as subarray. So you'll have to count down the number of subarrays which has exactly, very important word, which has exactly k different integers. Let's pick up one of the subarray. If I pick up this subarray, how many different integers it has? 2. That is 1 and 2. Can I pick up this subarray and count it into my answer? I cannot, because I need exactly 3. Exactly 3. Can I pick up this one? No, I cannot. Why? Because this has 4 different integers. 4 different integers. So this also cannot be counted. Can I count this one? Yes, I can count this one. Why? Because this has 3 different integers. Perfect. I got 1. Can I count this one? Yes, I can count this one. Why? Because it has exactly 3 different integers. That is 1, 3 and 4. So this can be counted. I got 2 different subarrays. Can I count this one? Yes, I can, because there are 4 numbers, but there are 3 different integers. So thereby this can also be counted. In this particular array, I can see that I have 3 different subarrays, or 3 subarrays with k distinct integers. So the answer is 3, and that is what you will be returning. Now what if this problem comes up in an interview? The extreme naive solution that I can think of is, I'm hearing subarrays, right? I'll be generating all the subarrays. Yes, that's the extreme naive way. I'll stand at 1. That's my first subarray, the number itself. Then I'll take 1, 2. Then I'll expand and take 1, 2, 1. 1, 2, 1, 3. 1, 2, 1, 3, 4. So basically 1 as the first element, and I keep expanding on the right. And after that I can stand at 2, and then I can keep expanding. So I'll be basically generating all the subarrays. And I'll be counting down those subarrays where the number of different integers is exactly k. Very important. So let's quickly write down the pseudocode. Again, we will be starting off from 0th index and we'll be going on till the nth index. Every element can be considered as the starting element. You can define a map which is going to store all the elements so that you can keep a count of how many different integers have you seen till now. After that, you can basically start from the index I and keep on adding elements till the last index. And what you will do is you'll go to the map and you'll say nums of j, because that is the element that you're adding, and you'll do a plus plus. Once you have done that, can I say if map.size is equal to k exactly, that means I have k different numbers. And if that is the case, you can do count equal to count plus 1, and initially we can have count equal to 0. And if very important, it's a small condition, if mpp.size exceeds k, there is no point in going to the right and adding elements, because if it has exceeded k, it cannot come back. So what you can do is you can break out. So that will be the end of the for loop, and that's it. And you can return the count. Again, what will be the time complexity? Can I say that the time complexity will be big O of n square near about? And if you consider hashing, that can go till n square log n. What about the space complexity? Can I say the space complexity is big O of n at the worst possible scenario? Why? Because I have numbers. If all the numbers are unique, the map will end up storing all the numbers in it. And if it stores all the numbers, the space complexity will be big O of n. Now this is where the interviewer will not be happy, because we are using n square and he'll ask you to optimize. So we are looking to optimize n square. That means I should be thinking of a solution which is around big O of n. And if that is the case, and the problem is having subarrays in it, which algorithm? Yes, 2 pointers should come to your brain. But this is not a typical 2-pointer problem. Why? Because we're not asked to return the longest subarray. Rather, you'll have to count down the total number of subarrays. It is slightly different. So what I'll do is, I'll start with a typical two-pointer approach, which is taking the smallest window, expanding, and then deleting. And we will see why that doesn't work. I'll try to figure out an algorithm that kind of works. Again, very constructive. It's not an algorithm. It's more like a constructive thing. So what I will do is, I'll keep L, I'll keep R at the first segment, which is this one. And at the same time, we will be taking a map data structure, which tells us how many elements, how many different elements we have. First number is 2. So the first thing you'll do is, you will enter it into the map. So what you'll do is number, comma, frequency. That's what you'll store. Number, comma, frequency. Please store that. Perfect. So as of now, can I say that for this segment, the number of different integers is 1. So I cannot count this subarray. Perfect. So what I will do is, I'll take R and I'll move it to 1. The moment I move it to 1, I will put it into the subarray, put it into the map. So this time my segment is this. Can I count this subarray? The total number of different integers is 2. I cannot count it. If I cannot count it, I'll move R. I'll move R here. So when I move R here, the frequency gets updated. This time, can I count this subarray? No, because it still has 2 different integers. So what I'll do is, I'll take R and I'll move ahead. Again, I have 1, so I'll increase the frequency to 3. Again, I cannot count this segment. So what I'll end up doing is, I'll take up this R and I'll move it over here. So when I move it over here, we have a 3 and I'll put it into the map. This time, this particular subarray can be counted. Why? Because it has exactly three different integers. So what I can do is, I can have a count variable which is going to store 1. Okay. After this, what I'll do is, I'll take the R and I'll move it here. So I'll insert 4 into the map. Now I'm asking a question. Can this segment be considered? And it is saying that it has 4 different integers, which is more than what I require. And if it is more than what I require, that means the window has grown in size. And if the window has grown in size, I'll have to reduce. So if I have to reduce, I shrink down the window. I take out the 2. So if I take out the 2, what happens is, the 2 goes off, because the frequency of 2 will be 0. 0 means you'll have to take it out of the map. So if you take it out of the map, the L will move ahead to this portion. Now you're asking, hey, listen, will this window be valid or not? And yes, because the map has 3 distinct elements. So this is valid. So what you'll do is, you will end up counting it. And after this, you will straight away take R and you will move it here, right? And you'll ask, hey, by the way, please make sure you increase the frequency of 3. I've increased the frequency of 3. I'll be asking, hey, is this window valid? And the answer that you get is, okay, is this valid? Yes, it is valid, because I still have 3 different integers, which is 1, 3, and 4. I still have 3 different integers. So you'll end up increasing the count. But what happens is, when you move this R, you're actually losing out on a lot of subarrays. Which are those? So previously, you did consider this, right? Can I not consider this? I can. Can I not consider this? I can. But you missed out on it. So it is not sure that whether you should move the R window or you should shrink the L further. It is not sure. So you'll have to be careful about these things. So whenever you are not sure about shrinking or expanding, that is when you start thinking of some different approach. Now, what if I just change the problem statement? I'll be changing the problem statement. And I'll change the problem statement to, can you count the number of subarrays where the distinct or different integers are lesser than equal to k? I'm changing the problem statement from equal to k to lesser than equal to k. Can I solve it? I'm not sure. But again, I'll try to do the standard sliding window and see if I can correctly expand and correctly shrink. So what I'll do is, I will take an L, I'll take a R, and at the same time, I'll be taking a map data structure which will be keeping a count of the number, and again, number, comma frequency is what the map will be storing. So I have the first segment. So I can insert it into the map and I can keep a count. Remember, we are trying to find out number of subarrays where the different integers are lesser than equal to key. Okay, so this is the segment. I'm like, can I consider this segment? Why not? Yes. So my count will be +1. And right after this, you know why it is +1, right? Because it has one distinct integer. It has one distinct integer which is lesser than equal to 3. Thereby. Perfect. The next thing I'll do is, I'll just take on this R and I'll move it here. So I have a 1. I'll take that 1 and I'll put it into the map. This time I'm asking, hey, is this segment a valid one? How do I know? Because the number of distinct integers is 2, which is lesser than equal to 3. So this is also valid. But, I'm saying this entire segment is valid. But am I missing out on a subarray? I am. The one itself. So whenever a new element is added, it actually creates a lot more subarrays. That is 1 itself and then 1, 2. Got it? So what I'll end up adding is +2 to it. So it will be 3. You'll understand as I keep moving it. I'll take the R and I'll move it here. So when I move it here, the frequency increases. Now what I'm asking is, hey, is this segment valid? And this is a valid one because it still has 2 distinct integers which is lesser than equal to k. So what I'm trying to do is, okay, I've added one more 1. So what subarrays am I generating? What are the new subarrays I'm generating? 1 itself because it has one distinct integer. This one also. And this one also. Now why are all the subarrays valid? If the largest subarray is valid, all the subparts of it will be valid. Obvious. That is why the 1 will be this, then it will create this, then it can create this. So I can actually add 3 more to the answer. So I'll add 3 more to the answer, so that will be 6. What I can do next is I can take R, and take it to the next one. So the frequency increases to 3. So again I'm asking, is this valid? Yes. So all the smaller parts in it will be valid. So this 1 will end up creating 1, 2, 3, 4. So you can add a 4. So I can actually create 10 subarrays where the sum is lesser than equal to k. Perfect. I'll take the R and I'll move it to 3. So when I move it to 3, I have a 3 which is of a frequency 1. I'm asking again the same question. Is this segment valid? And the answer comes up, yes, this is a valid one. And if this is a valid one, the 3 can form all of these subarrays. So in total, it can actually form 1, 2, 3, 4, 5, which is nothing but the length. So I can increase it to 15. Now what is the next thing? I will take R and I'll place it here, which is 4. 4, 1. Now this is the moment I'm asking, hey, this is the segment. Is this a valid segment? And it says, no, this is not a valid segment. Why? Because when I look over it, it has 4 distinct integers and I'm looking for lesser than equal to, hence not valid. And if it is not valid, to shrink down the window. Because if the longer segment is not valid, I cannot be sure how many subparts will be valid. So what I will do is, I will trim down 2. So the moment I trim down 2, what happens is that 2 goes and the L will go 1 step ahead. So when the L goes 1 step ahead, this is the new segment. And if this is the new segment, I check it out and it says it is valid because it has 3 distinct integers. And if the bigger subpart is valid, I've added this element. This was the new element that was added to the window. Thereby, A itself, including till only here. And how many are there? 5. So you can again add it. So that will be 20. You can keep on doing this till the R crosses the boundary. You can keep on doing the dry run. I'll not be emphasizing on it. So we have kind of solved a part of the problem. So what I will do is, without wasting time, I'll try to write down the pseudocode for this one. Okay. So what I'm trying to do is break the problem down into sub-problem and then try to solve it. So nums and you're given k. You obviously will take L equal to 0, R equal to 0, and there will be a counter equal to 0. Remember, we are trying to solve the problem for lesser than equal to k. Number of subarrays whose sum is lesser than equal to k, because we can be sure whether to move left or whether to shrink or whether to expand. We're very sure for this one. Okay. Next thing, we'll be requiring a map. So you can take a map. Again, I'm writing down the pseudocode. In case you want your language specific code, you can find them below. So what I will be doing is, I'll be running a while loop, standard sliding window, and it will be going on till nums.size, or you can just store it in n variable. What you'll be doing is, okay, mpp nums of r plus plus. Perfect. What after this? I know one thing. The segment has to be valid for its subpart to be valid. So I'll keep a check. Hey, if mpp.size segments the number of different integers, is that lesser than k? If this is not valid, and you keep on shrinking. So I'll be writing a while loop. And I can straight away go as mpp nums of L minus minus, and you can do L equal to L minus 1, and not here. Maybe before doing that, what you can do is, you can keep a very simple check. Hey, if map doesn't contains this, please ask the map to take off this element, and it will be doing it. So you can just erase it. Perfect. And then you can do a L equal to L minus 1. Now once you've done this, you can complete the while loop. Done. Now you surely know that the segment L to R has exactly k different integers, right? So the reason being, the minimum value of k is 1. So you're very sure that this will happen. After this, what you can do is counter equal to counter plus the number of subparts that you were able to create with the new element was R minus L plus 1, the length. So you can just add it, and then you can take R and you can say R plus 1, and you can end up the while loop, and then you can straight away return the count, and that will end up the function. Okay, so I've solved the problem for number of subarrays where the different integers is lesser than equal to k. But wait, I need it for equal to k. So can I actually solve the problem 2 times? I'll say, okay, I'll find out the number of subarrays for lesser than equal to k, right? I'll find out that one for lesser than equal to k. And I'll also find out for lesser than equal to k minus 1. I can also do that because I know the algorithm that finds out. So I'll be finding out for lesser than equal to k minus 1. Now, if I have the number of subarrays for lesser than equal to k and for lesser than equal to k minus 1, how many will be exactly equivalent to k? You heard that correct. You can just subtract. You can take this answer, you can take both of the answers, and you can simply subtract. So what you'll do is, you'll call the function like nums with k minus func nums with k minus 1, and that will be your answer. Can I derive the time complexity? I can. There's a while loop on which it is dependent. I can say this is taking a big O of n. There is again an inner while loop where you are comparing and shrinking the window. This throughout the course of time will be taking big O of n. I've already done it in a lot of times. I've already explained it a lot of times in the 2-pointer playlist. So can I say that the overall complexity for the worst possible scenario will be big O of 2n? Again, assuming that the map works in in constant time, and the space complexity over here will be big O of n. Why? Because we are using a map data structure, and the array contains all the unique elements. all the elements are unique, you'll end up storing all elements of array into the map. And the overall time complexity will be 2 times of it. Why? Because we're calling it once for this, once for this. So the overall time complexity and space complexity will be 2 times of this. So I hope you have understood this one. So that will be it for this video. So if you're still now watching and if you've understood everything, please do consider giving us a like. And if you're new to our channel, do consider subscribing to us as well. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye. Take care.
Whenever your heart is broken, don't ever